This is our PreLab video for our reaction, which this week is an aldol condensation reaction. It's going to introduce a new kind of chemistry, involving a negatively charged carbon, a carbanion. We've dealt with carbanions before with terminal acetylides, which we used as nucleophiles, and with organometallic compounds, like an alkyl lithium, that we could also use as nucleophiles. And note, in this case, it says this is an aldol condensation. So a condensation is a particular kind of reaction where two molecules are put together and water is produced. So in this, we'll also have to explain where the two water molecules are released, because it is the release of this water that really makes it a condensation reaction. So a condensation reaction is a reaction that brings together two molecules to make one molecule, while at the same time removing water in that reaction. So if we're going to talk about carbanions, we need to remind ourselves about the pKa's of different groups, right? We know that alkanes are really weak acids, right? And so therefore the carbanions, right, the anionic conjugate base of alkanes are really, really strong bases. It's why when we made organometallic compounds, we had to keep them away from anything protic, because this is so basic. It will steal hydrogen ions from almost anything, right? Water is a much weaker acid than an alkane. Alcohols are much weaker acids, right? So if we're dealing with alkanes or alkenes, they're really, really, really weak acids, and the carbanions are really, really, really strong bases, and we had to deal with that. Sort of the first groups that we made under moderate conditions as carbanions were the terminal acetylides, right? And for those, we could use the amide ion as a base to deprotonate it. But there's a unique situation when we have a hydrogen on a carbon next to a carbonyl group. Even if that carbon is sp3 hybridized, like an alkane, that is, for a carbon-hydrogen bond, unusually acidic. And so it's in the range of alcohols and water in terms of its strength as an acid. And so it can be deprotonated to create a carbanion. And then, like other carbanions we've made, that carbanion can be used as a nucleophile. And so that's what we're going to do today. So, if we look at this, this is a strong enough acid that we can use, a base like the hydroxide ion to deprotonate it, and we get water. Now note, water is still a stronger acid than the hydrogen next to a carbonyl. And so the equilibrium for this reaction lies toward this direction. But all we need is enough yield of our carbanion form, which will be our nucleophile. And so we don't have to get 100% yield. We just have to get enough yield of our carbanion form so that we can have enough nucleophile that the rate of our reaction will be acceptable. And since this is an equilibrium, right, we can bring in right? Our second favorite dead French chemist, Le Chatelier, right? And so as our reaction consumes our nucleophile, right, that stresses the equilibrium, and that will pull the reaction through toward completion. Now, just to show why this carbanion is more stable than we would expect, right? If this pair of electrons falls here, and the pi electrons go up there, we can get an alternate resonance form, right? And that resonance form looks like an enol that's been deprotonated. We call that an enolate. And the enolate form is actually more stable than the carbanion form because the negative charge is on a more electronegative atom. And so part of the reason we can deprotonate our hydrogen or our carbon next to the carbonyl is that the carbanion form is stabilized by resonance with this more stable enolate form, right? And so it is that enolate form that helps us accomplish the reaction we're accomplishing. Now, we just said the enolate form is the more stable of the two resonance forms. But if that's the more stable form, then that makes the carbanion form the more reactive form. And so that's the one that continues the reaction. And then once we've created our carbanion form can act as a nucleophile, and we're going to react it with another carbonyl compound, an aldehyde. The oxygen of an aldehyde is more electronegative than the carbon. So the carbon is partially positive. So the carbanion nucleophile can attack the carbon. The pi electrons move to the oxygen, and you get a tetrahedral product ion, right? That's a common result when you attack an sp2 hybridized carbon of a carbonyl with a nucleophile. We get, right, that same atom ends up being sp3 and tetrahedral in the product. And then if we can protonate that, right, if we can protonate that, there's water around, then we can get a beta hydroxycarbonyl compound. That is a compound that we can call an aldol, right? So if we look at our carbonyl, right, there's a carbon alpha to the carbonyl and a carbon beta to the carbonyl, and that carbon beta to the carbonyl has a hydroxyl group on it, right? So this beta hydroxycarbonyl compound is something we call an aldol, and hence we call this the aldol reaction, right? So where a carbanion, a resonance stabilized carbanion next to a carbonyl, right? A resonance stabilized carbanion next to a carbonyl attacks another carbonyl compound as a nucleophile, giving this product, a beta hydroxycarbonyl compound. That's our aldol. That's the aldol reaction. Now, note, that's the aldol reaction. Later we will have to account for, right, where does the water come from that makes this a condensation, right? We'll have to explain that when it's time, okay? Now, I know a lot of people are taking this class they want to use organic chemistry as a mechanism to learn about biochemistry. And so alpha carbanion mediated reactions like that are important in biochemistry. Many bond making or bond breaking reactions in biochemistry involve these stabilized carbanions next to carbonyls that can form enolates in resonance. So one example here, this is a reaction that we see in glycolysis, the splitting of fructose 2,6-bisphosphate. And so in that, note that we have our carbonyl, right? We have our alpha carbon, we have our beta carbon, and on that beta carbon is a hydroxyl group. Thus, fructose 2,6-bisphosphate is an aldol. And so it is the product of, it can be the product of an aldol reaction. And so we can also then reverse the aldol reaction. And so, if the stabilized carbanion can act as a nucleophile, then at least under the conditions that enzymes create in biological systems, that stabilized carbanion can act as a leaving group. So if these electrons can fall here to make a carbonyl, and these electrons can leave with this carbon, then we get, right, with loss of a hydrogen ion, right, there has to be a base around to take this extra hydrogen ion, but with loss of that hydrogen ion, we can get, right, our carbanion that was a leaving group and an aldehyde as product, right? And so if you've studied glycolysis, you've heard of dihydroxyacetone phosphate. This is the carbanion form of that. And you've heard of glyceraldehyde 3-phosphate, right? And here's the dihydroxyacetone phosphate carbanion stabilized by resonance with its enolate form, right? So here's that resonance stabilization. If we show the electron movement in that resonance stabilization, right, these electrons can fall here to make a pi bond. These electrons come here, and you get this as the product. So these carbanion-mediated reactions in terms of making carbon-carbon bonds or breaking carbon-carbon bonds in biological reactions, that's probably the second most important set of reactions from organic chemistry that we can carry into biochemistry. There are lots of nucleophilic acyl substitution reactions, and now we can talk about carbanion-mediated bond-making and bond-breaking reactions as being really important in biological processes. Okay? So, here's the mechanism of the reaction that we're going to carry out. Right? So we've got, right? We're going to use the hydroxide ion as our base in a mixed alcohol-water solution. Okay? And so our hydroxide ion is our base attacking a hydrogen on the alpha carbon. The electrons from that hydrogen on the alpha carbon go back to that carbon to create our unshared pair on our carbanion. Note that water would be the other product not shown. And also note that this is an equilibrium reaction, and the equilibrium reaction still lies very far toward the reactant side. Right? We get a low yield of our carbanion, even with the resonance stabilization. Right? Now, our resonance stabilization can also occur, and you should be able to show that, where the unshared pair of electrons falls in to make the second bond with the carbon, as the pi electrons from the oxygen are moved to the oxygen, and this transfers the negative charge to the oxygen. So the negative charge is shared between the oxygen and the carbon. That stabilizes the carbanion, and it's stabilized even more because there's one form where that negative charge is on a highly electronegative atom. Right? We can consider the reverse resonance, where the electrons fall back to form the pi bond, and the electrons come back to the carbon to create the carbanion. Right? So that's the part of your mechanism to create your nucleophile for the attack on the carbonyl. Okay? Our carbonyl compound that's going to be attacked, we're going to use benzaldehyde. Right? So this is benzaldehyde. You should make observations about both what it looks like and with benzaldehyde, what it smells like. It has a very distinctive odor that you should note in your observations. Note benzaldehyde, if we're focusing on this question, right, it can't be deprotonated because there are no hydrogens on this carbon next to the carbonyl. So it's not going to react with the base like your acetone is. Right? And so, right, with carbonyls, as we said earlier, right, the oxygen is electronegative, so it pulls the electrons in the carbon-oxygen bond, so it becomes partially negatively charged. The carbon becomes partially positively charged, and therefore it becomes a good electrophile. And so there are lots of situations where a nucleophile, an available nucleophile, will attack the carbon of a carbonyl and open up that pi bond to create that tetrahedral carbon, that tetrahedral intermediate. And then under the conditions, right, that tetrahedral intermediate is technically still an alkoxide. Right, which we know is a relatively strong base. Right, and so that alkoxide can react with other things in there, including water. Right, the alkoxide group is protonated, making then our, right, if this is our carbonyl, right, there's our carbonyl, right, there's our alpha carbon, there's our beta carbon, so there is our beta hydroxyketone intermediate, right, this is our aldol product. Right? So that first step is our aldol reaction. Now, the problem is aldol products themselves are reactive under these conditions. And so it's really difficult to get this reaction in solution to stop at the aldol product. Remember, biological reactions accomplish it by doing the reaction not in solution, but isolated from solution in the active site of an enzyme. So they can stop reactions at the aldol product. Under the conditions we do them in solution, the aldol product is still susceptible to reaction. So we need to look at that reaction now. Right? So, right, here's our aldol product. And note, right, if we look at this, right, we still have a carbonyl. Right? We still have a carbonyl. And so here is our, right? Here's our alpha carbon and our beta carbon. Well, we still have hydrogens on an sp3 hybridized carbon next to a carbonyl. That's the same situation we started with. That carbon is still more acidic than we might expect. So under the basic conditions that we're using here, more of the base can deprotonate that alpha carbon, but when it's deprotonated, instead of just going back to the alpha carbon, those electrons can fall, and we get an elimination, but with the hydroxide ion acting as a leaving group. So this becomes an E2 type elimination. But using something that we're not used to seeing as a leaving group, right? A hydroxide ion acting as a leaving group. But in this case, the reaction is neutral. We've got a hydroxide ion as nucleophile, a hydroxide ion as leaving group. But what really promotes this reaction is that our product, we'll go this way, our product, right, this new pi bond we create in our product is conjugated with the pi bonds in the ring and with the pi bonds in the carbonyl. And so by linking those two conjugated systems, it creates a longer conjugated system, and that longer conjugated system is more stable than the isolated systems are by themselves. So in part, it's the stability of creating this new bond that is both conjugated with the existing pi bonds and that connects all of those pi bonds into a uniform system of pi bonds. It's that stability which ultimately drives this reaction forward. The stability of this new pi bond in conjugation with and connecting all of this into a single pi system. Right? That's the driving force. Now, note at the end of this, on the other side of our molecule, we have another carbon next to a carbonyl, and we are still under basic conditions, right? And so a reaction just like the one we've done, right, are repeated on the other side to get the complete product, right? And so use the same model to develop a mechanism and to complete your mechanism for the reaction of another molecule of benzaldehyde with the other methyl group that we've got here. Right? Now, thinking about what we just said, right? The final product, right? We're going to start with liquids that are colorless. So observations are going to be important here. So as you're doing your work in lab, you're going to want to, you really want to record observations about what things look like. But we're telling you this final product has a color. So what we want you to do is go back and think about the chapter we just finished and the trends. The trends in UV visible absorbance and structure, right? So look at the structure of your product and go back to the chapter on UV visible absorbance and use that to explain why we generate a product that has a distinct color from starting materials that are both clear. Okay? So Notes on the procedure. We're not going to make any changes from the procedure as it's presented in the text. Right? Now, a couple of notes. Right? We are using sodium hydroxide at a relatively high concentration in a solution that includes both water and ethanol. Right? So this ethanolic sodium hydroxide solution is very basic. Right? And we know that working with bases is really more difficult and more dangerous than working with acids because bases don't burn when you get them on your skin. Right? The most you'll feel is maybe a slick feeling. So again, right? This is one you should keep your gloves on when you're handling the basic solution. But if you do notice that your fingers are feeling slick and you think you might have come in contact with a base, it's not something you panic about. Just go to the sink, run copious amounts of water over your hands. Just let it run for 15 or 20 minutes while you're having a calm conversation with whoever is around. Right? It's not something that would cause a panic, but if you do feel like you got base on your skin, just make sure you run enough water to pull whatever base might have leached down into the layers of your skin out of your skin. Right? When the text calls for a small Erlenmeyer flask, we don't want it to be too small. You want to be able to swirl without splashing the strongly basic solution out. So we found that 125 milliliter Erlenmeyer flask is appropriate. Now, this reaction goes very quickly, so we should have time for recrystallization next week. Now remember, the lab text suggests using 20 milliliters, approximately 20 milliliters of ethyl acetate for recrystallization. Remember, right? How do we determine the minimum appropriate amount of solvent for recrystallization, right? Don't forget your procedure. I do not want to see anyone just measuring 20 milliliters of ethyl acetate out and dumping it into your isolated crystals, right? Again, pay attention. Mr. Wyeth will have notes up about disposal, so pay attention to the way you're disposing of your non-aqueous organic wastes. I hope the video is helpful. If not, please ask questions. Please, make sure you're prepared for lab work this week.